These are basically the formulas that I expect you to remember from part 2 of the class. However you want to remember them is fine. So our first question there is, what's the neutral point? And they give you these plots, and you can pick any one of these things. You might as well pick the one that goes to CL equals 1. So if you can focus over there on the plot that goes to CL equals 1 on the diagram on the board, I'm right there. So I come up and I see 15. So this is 0.15, and I know immediately that my KSM is equal to what? Is equal to minus 0.15 is the slope of the curve. 15% or 0.15, right? The 15% static margin. So where's the neutral point? Well, I want the neutral point. So if I wanted the neutral point, I need to know the CG position. Well, that's given to you. Your XCG is given as part of the problem as 0.N4 or 0.0N4, and add it to my static margin, and that's going to be a bigger number. So my aerodynamic center is going to be bigger than static margin. That means that it's aft. So if my center of gravity position is here, then based on this design, my neutral point will be aft, and I'll have a stable airplane. A stable airplane means that my tail will be downloaded. The tail is going to subtract some of the lift the wing has to generate, because that's a stable airplane. If I have an unstable airplane, I have an uploaded tail. That sounds good, except it's very hard to fly that. Situation right now is people are designing, where should I design for the Global Hawk? What kind of stability should I give that airplane, right? And if I was in one of those meetings, you'll be my, you'll say, why would you want to make it more than neutrally unstable? Just unload the tail. That gives you a very small tail or no tail, right? And then if you lose power or if you lose some control over the airplane for some short period of time, it's not going to disintegrate. Because don't make it highly unstable. There has to be a reason to make it highly unstable other than you can do it because of the respective instability things. Stability coefficient is Cm alpha or M alpha, right? For lateral stability, it's M beta. What kind of a pitching moment do I have if I have a positive alpha? It's got to be negative. Cm alpha, M alpha. So you can work the same reasoning for the rudder, for N beta. M alpha, N beta are the static stability derivatives. I see that Cm alpha equals minus KSM times CL alpha. I know minus KSM is 0.15. Do I know CL? And what sign should it be? Well, the lift curve slope is always positive. If it's a stable airplane, you're going to end up with a negative, right? You're going to end up with, if KSM is 0.15, minus will be a negative number. So your Cm alpha has to be negative. C sub L, so what have I got? I've got this system over here. I've got a stall line shown like this, and I want to put this point in trim, CL land. And that CL land is 0.92 is going to be aft of the stall line. Okay. So here's the question. Your CL is going to be aft of the stall line. So my question is, can I do that? Can I do that? What you got to do is to unload the tail. You got to download the tail, taking up some of your lift. So you move the CG aft to unload the tail, all right? And then you might be able, so how would I do that on that curve? Well, if this is my CL land, then I would come down to this point on the stall line, right? And then draw a line from the origin. And then this slope, that change in slope, so the delta slope will be what percentage I move the CG aft. If I move the CG aft, then I will put that point in trim. At what elevator deflection? Well, I have to look at the chart. I look at the chart over here, and I see that the elevated deflection for 0.92 looks like 0. So this guy is going to be the 0 elevated deflection. Is going to come in like this. So this will be delta E equals 0 line. So at 0 elevated deflection, I'll put this point in trim. If I move my CG aft, I that one. That's the bottom of your trim triangle. That's the bottom of the trim triangle. And the trim triangle can never go after the neutral point, right? So there's some limit between, I can't just say, oh, I want this C-sub-L, I'm going to go down here, I'm going to intercept down here, right? Because that slope will probably be past the neutral point. So you'll be flying an unstable airplane. You'll be putting the lift on the tail. So this is your bottom of your trim triangle. Where's the top of the trim triangle? Well, the top of the trim triangle is how far can I move the CG forward. So this is the delta slope aft, and this is delta slope forward. Forward. And that means that if I move the CG forward by that percent from what's given down those charts, this will be my, I'll have to go faster. I'll have to go faster. And I always ask the velocity. If I move the CG forward 10%, what's the fastest I can, what speed do I have to land the airplane at? So you take this landing speed, and you got to change it to that landing speed for that C-sub-L. And you would do that using C-sub-L equals W over S over Q bar. Your speed is embedded in the Q bar. So you'd have to land faster to get a lower C-sub-L at the same weight. Or what weight change would I get? How much would I have to lower the weight to move the C-sub-L if I move the CG 10% forward? Bottom line is, that's my trim triangle. It gives me the range of control deflections and CG positions with the stall that I can put into trim. I can trim anything that's inside this trim triangle. This alpha stall line is only good at the CG position, XCG. It's only good at the CG position given. It moves when you change the CG. It moves with the CG because you're loading and unloading the tail. You'd see that on the CL alpha curve. But rather than do all that complicated shenanigans, Roscom's genius was draw the trim triangle. And it moves the CG, it moves it for you. So actually the stall line is actually moved back over here. It's moved back for aft CG, and the stall line is moved over here for a forward CG. And you're allowed the limits forward and the limits aft based on what kind of airplane it is and how I'm going to load it, right? And where my neutral point is. What is my static margin for this thing? Give me CM delta E. Give me elevator control power from this graph, CM delta E. CM delta E means you have to hold alpha constant. Okay? By definition, it's a stability derivative. It's a partial derivative. You have to hold alpha constant. So you have to be taking the CMCL along that alpha line. Like this point here, at that elevator deflection, then go down here, take this point here at that elevator deflection, and you'll get a different answer by 30 or 40, 50% different. CL delta E would be another one. You can get CL delta E off this curve. And I'm not going to show you how to do it. Right? But that'd be a great question to ask. Give me CL delta E. So I want two different C sub L's at two different delta E's on this curve. You see the stall line? Stall line's at delta equals 0, yes? So I can put the stall line in here, and I know the stall is going to be about 0.36 radians. That's the stall alpha, yes? So if that's the stall alpha, I can go up here and take on the stall line a minus 15. So I come down here to the stall line, and I draw a parallel line, and that's going to be minus 15. So I can draw another line. I've got the delta E equals 0 line, and I can also draw the delta E equals minus 15 line by projecting the stall line back on this curve, and I'll get this. And now I can take these 2 points and compute C sub L delta E.
All right, this last problem asks us to set up the Kramer's solution, which is shown here for theta to delta E. And we can see that from the state vector, theta is the third state. So that's all we need to remember. And the Kramer's rule is going to look for the characteristic equation and the coupling numerator. So the ratio of the numerator to the del long will give us the transfer function. So the last problem asks us to solve for the state space transfer function. So let's see how to do that. State space is given by x dot equals ax plus bu. This is the standard form for state space, where the state space vector has been defined on the previous page, where we said the x was equal to, and I don't remember the exact states, but the third state was, actually I think it was u, airspeed, angle of attack, alpha, and then q with the 4 states. So if we take the Laplace transform, then the x dot becomes Sx in the Laplace transform. And these variables just become variables of s. Then I can factor the x on the left-hand side of the equation, and that will give me si minus a, x of s equals b delta e. And this is the form that we've solved this equation using Cramer's rule. So we know that x3 over del, where x3 is the third state in our vector x, equals the numerator and theta delta e over del long. So the problem then just becomes now finding out what si minus a is. Well, si is simply an identity matrix times s. So I have s's, s, 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 and everything else is a 0 on the off-diagonal term. That's s times I. So we can see then that si minus a would take the A matrix, which is given up here, and just put a negative sign on all the elements to get minus A, and then on the diagonal put the s's. So we have si minus A would be s on the diagonal, first diagonal, and then it would be plus 0.05. And that would be si minus a, where that term is. All the off-diagonal terms would just be the negative of the A matrix. 18.7, and then 0, and then minus 0.0024, and I think you get the idea. The diagonal terms are going to have, however, s plus 2.8, or 2.8. So that's how you're going to make the si minus a matrix, which is this guy. And the determinant of that matrix, the determinant is going to be del long. Is going to be del long. If I take the b vector, which is shown right here, if I take that b vector and substitute it for the third column, for the theta, that's going to be the coupling numerator and theta delta e. So the determinant of the si minus a matrix with the third column replaced with the b will give me the numerator. And that's the answer that this system is looking for. We are looking for these two terms, and that should take care of this question. For the levels and categories that were available from the tables for the short period and the phugoid. So you need the damping, basically the damping to do this from the short period and phugoid modes. So how are we going to get that? The system gives you the eigenvalues and the eigenvectors, but for the damping we'll need the eigenvalues. It's pretty obvious that this is going to be the short period mode, the faster one, highly damped, and then the phugoid, the long period, is going to be this one. Well, if we have the imaginary part, right, and that's given by, let's look at the phugoid. The imaginary point of the phugoid is going to be 0.17, and then we have a real part, a negative real part that looks like minus 0.02. 0.02 squared plus 0.17 squared square root will be omega n. And once I know sigma and omega n, then the cosine, or the 0.02 divided by omega n, will be the zeta. So that's how you will figure out the zeta for both the phugoid and the short period. And once you have that zeta, you can compare it with these values that are given over here to see if it's level 1, level 2, or level 3.